Today we'll talk about kinetics of multi-step reactions. So, a simple multi-step reaction might be 2 protons plus 2 electrons goes to H2. It's very unlikely for 2 protons to hit the surface at the same point at the same time and 2 electrons to simultaneously hop on them and form a bond, right? Very unlikely, so that's not what happens. That's not what nature does. What is found is, as I mentioned before, the rate depends on metal surface that catalyzes the reaction, and the reaction goes through a metal hydride intermediate. And so it's the bond strength of that metal hydride intermediate that affects the overall rate of the reaction and which step is rate determining. So that's just an example. Another, something you might run into here, imagine I have a transition metal like tin 4+, right? Tin 4+ can undergo a 2-electron reduction, a 2-electron reduction to form tin 2+. Again, although you only require one tin 4+ hit the electrode, you will never go through a process where the 2 electrons transfer simultaneously to give you tin 2+. Right? So it's always going to be a 2-step reaction. So it's not possible for both electrons, well, it's possible, it's very improbable to transfer simultaneously. So how does this work? So let's think about this. Usually one of the steps, if you have a series of individual steps in a mechanism, right? What determines the rate of the overall process? How do we think about the rate of the overall process? Okay, each step is going to have its own activation energy. Are all the activation energies going to be the same necessarily? No. So which step do you think is going to determine the rate of the overall reaction? The slowest step, right? So if we have a line of students taking buckets of water and trying to put out a fire, and we're carrying really big buckets, and I hurt myself and I can't move them very fast, and you guys are handing me buckets, but I can only move them at a certain rate to dump out the fire. Like, no matter how fast the buckets come to me, the buckets are only going to get on the fire based on how fast I can dump them, right? So I'm the rate determining step, right? So same thing in the kinetics. So let's write an expression for electrochemical reaction with n electrons. And since electrons transfer one at a time, we need n steps at least. We might have more than n steps because there may be chemical steps that don't involve electron transfer, right? So any given mechanism, so these are two chemical reactions that we can formulate in this type of expression, will have at least n steps in the mechanism. These are elementary steps. So we can define n. So n, the number of steps, is going to be equal to n prime plus n double prime plus 1. So n prime is the number of electrons transferred prior to the rate determining step. N double prime is the number of electrons transferred after, to R ds, transferred after R ds. And this is, of course, the electron transferred during rate determining step, RDS. Now we can actually write our mechanism in terms of a series of electrochemical steps. So first, we're going to have O plus n prime electrons going to O prime. And this is the net result. So if I added up all the individual elementary steps that constitute the things that happen before the rate determining step, this is the equation I'd get of all steps prior to RDS. And then, of course, we have the RDS, the rate determining step, O plus an electron. Make these reversible. R prime, there's all the forward and reverse rate, right? And this is the rate determining step. And then I can similarly take all the steps that happen after the rate determining step and sum them together into a single expression to get the product R. And so this is the net result of the mechanism after the rate determining step. So what, my friends, is going to limit the reaction? 1, 2, or 3? What's going to determine the overall rate of the reaction?
2.
2. Okay, that's a gimme, right? The rate determining step. So the current, if I want to write the current now going through my electrode, driving this overall reaction, so the overall reaction is O plus N electrons going to R. So N is the total number of electrons transferred in the overall chemical reaction, is going to be N FA. So N is the total number of electrons transferred. NFA times our beautiful Butler-Volmer equation, CO prime 0 T, e to the negative alpha F, E minus E naught of the rate determining step, right? Each of these is going to have an E naught, right? I can write an E naught for every single one of these. Remember, because E naughts are just related to delta G's versus a reference reaction. So I can take any chemical half reaction, electrochemical half reaction, write E naught for it, even if it's a rate determining step, right? Or even if it's not a rate determining step, if it's any elementary electron transfer reaction, I can write E naught for it. And then what else do I need to put in my Butler-Volmer expression? What is this sort of part refer to? It's the cathodic current, so it's the reduction current, right? Or the forward current. The electrons transfer from the electrode to the electrolyte. And I need to subtract what? CR prime, right? Because this is the rate determining step. CR prime times e to the negative, e to the 1 minus alpha F E minus E naught RDS. Okay, so there's my expression for the current. And this is just Butler-Volmer for the rate determining step. Okay, so now the challenge is how do we express this in terms of things we actually know, right? And so it gets kind of messy. I'm actually not going to go through it because it's really messy. I have gone through it in class before. But if you think about it, we don't really want to put things in terms of E naught RDS, right? Because that's something we don't even necessarily know. Okay? And we also don't want to put things in terms of, sorry, there should be a 0T here, in terms of the intermediate concentrations, because those are, again, things we can't control experimentally. So it turns out what you can do, just like you often do in kinetics, you can make assumptions. If these reactions are fast, for example, we can write this concentration in terms of this concentration and the electrode potential and the E of this reaction, and we can use some tricks about the relationships between the E's of all these reactions and the total E naught for the overall reaction. And you can go through it in Barton-Faulkner. It takes about half an hour to write through all the equations. It's kind of messy, but the end result is actually very cool. And what you get, so let's write out just kind of what we do. So we want, just to get you the framework here, CO prime 0t and CR prime 0t in terms we know. We can assume, or one thing to do is assume other steps are at equilibrium. And so what you get is you get this equation, I over I naught equals CO 0t over CO star. Now these are O. These are not the intermediate concentrations. These are actually the concentrations of O are reactant, right? E to the negative n prime plus alpha F eta minus CR 0t over CR star E to the n double prime plus 1 minus alpha F eta. This is kind of cool because now we have an expression. We have an expression that captures the forward and reverse current for the overall system in terms of the number of steps before and after the rate determining step, and alpha for the rate determining step, and then the concentrations of O and R. So it's kind of just like a modified Butler-Volmer expression with a few extra parameters to account for it's a multi-step reaction. If you think about it, this step might have an E naught that is just much higher than the overall reaction. Remember, this is thermodynamics. Like imagine like one of my steps is putting a radical electron on an oxygen or something. That's going to be really thermodynamically unfavorable. It's going to have a very high E naught. And that will give me a large activation energy for the overall reaction. No, it does not show up in the overall reaction thermodynamics because that radical is an intermediate. So remember, this is thermodynamics, not kinetics. These are thermodynamics for the individual steps, but they kind of give you a framework to understand the kinetics of this reaction. But it's not even that simple because even these individual steps, this might have a very unfavorable thermodynamics, but it could also have a very unfavorable kinetics. So one of the things people do in electrochemical computation, using density functional theory calculations to calculate all these things, they'll calculate all the energies of all these intermediates, and they'll calculate the E naughts. But one thing they're not very good at is actually calculating the activation barriers for the individual steps. So you'll find this in electrochemical literature, a thing called a theoretical overpotential. And that's related to exactly what you just said, the E naught of the rate determining step. So, well, what you usually do is you flip this around and you measure some data and then you propose a mechanism and try to see if that mechanism is consistent with your data. We can reduce this expression in the case where mass transfer is fast. So what happens if mass transfer is fast? What happens to that expression? That the surface concentration of O and R has to equal the bulk concentration because mass transfer is really fast and the current is sort of small relative to the limiting current, right? So I equals I naught. So we're going to drop those terms, so those are going to go to 1, right? The surface concentration over the bulk concentration. So this is just the same expression. Eta minus E. What's eta again?
Overpotential.
Overpotential. What's the definition of overpotential? Eta is defined relative to the equilibrium potential, which makes sense, right? It's the kind of driving force you have to apply to the system relative to equilibrium. So let's go back to this equation. So now we have this equation, again, for overall. And we can even simplify this further. Assume eta is large. So what happens to this term if eta is large and negative? N prime is going to be an integer, right? Alpha is about half, right? F is a constant. If eta gets large and negative, negative times negative is what? Positive, so this term should go to infinity. What happens to this term? This is a positive number, integer 1.5, constant, large and negative, e to the negative value goes to 0, right? So of course that makes sense. If you have a large negative current, or a large negative overpotential, the cathodic part is going to dominate the anodic part. So okay, so then I can rewrite this equation I equals I naught, and I can just take the first term, e to the negative eta prime plus alpha f eta. And so this is basically a modified Tafel expression. What we can do is think about like what kind of data you might measure in the lab. So imagine you measure eta versus log I. Say you measure some data, right? So you fit it to a line. And say you get a slope equals 120 millivolts per decade. Right? But remember here, the slope, this is actually going to be related to this term. So from the slope, we can actually figure out, we can propose what n prime should be. So let's do that. So we can rewrite the Tafel expression, ln I equals ln I naught minus eta prime plus alpha f over RT eta. And then we can convert to log base 10, log I equals log I naught minus eta prime plus alpha f over RT eta. Okay. And this part here, what's f over RT? Do you guys remember? Oh, there should be a 2.3 in there somewhere. Yeah, 2.3 down here. Sorry. 2.3 RT. You guys remember what that is? So this is just 60 millivolts. And so what you can see is this whole thing, the Tafel slope is this whole thing, right? This whole thing is the Tafel slope. So you can tell if you have a Tafel slope of 120 millivolts per decade, eta prime plus alpha has to be equal to what? So actually, let's see, this is what I told you is not quite right? Because this is log I is x. This is y not, right? So if I plotted it with these axes switched, it would correspond to this equation. So the actual Tafel slope is going to be the inverse of this. But another way to say this, eta equals 60 millivolts over eta prime plus alpha log I naught minus 16 millivolts over eta prime plus alpha log I. Okay, now this is the Tafel slope. So if 120 millivolts, if we measure 120 millivolts, right? So that's what we measured. This is say experiment. And we say that's equal to 60 millivolts over n prime plus alpha. I think I've been saying eta prime or something, but it's n prime, right? It's the number of steps preceding the rate determining step. Then, and I assume alpha equals 0.5, then this means eta prime equals 0. So that means the first step is rate determining if you have 120 millivolt Tafel slope. In principle, this is all within the context of a lot of assumptions and, but this is kind of classical electrochemical kinetics, how people will analyze these equations. It's good to understand it. But understand that it's all couched in a lot of assumptions, and so the reality is, one of the challenges about Tafel slopes is this predicts actually, if you assume alpha equals 0.5, it predicts very precise numbers for Tafel slopes. Mm-hmm. But in fact, people find Tafel slopes that vary continuously. Some very well-defined reactions go by 120 millivolt Tafel slopes, and they really look like one electron transfers, and it's really pretty well fits this theory. But a lot of reactions, for example, that we're interested in, like are inner sphere reactions. So what inner sphere means, we'll talk about that next, but it basically means that the reactant absorbs on the electrode surface before the electron transfer takes place. And the whole model for how that happens is very different, because we had this whole model of, remember we had our electrode and we had some double layer here, right? and that move this energy up and down relative to some E solution, right? But if the thing, that assumes that the electron transfer is transferring through the double layer. This whole model assumes the electron is transferring through the double layer. But if you have some absorbed species right in the middle of the double layer where there's a very strong electric field and the electrostatic potential is not well defined, or it may be changing, it gets a lot more complicated. But that's an area where we don't really understand precisely simple analytical models to describe electron transfer in those contexts. I mean, you can write down models, you can write down lots of models, and that's fine. But it's harder to compare with the experiment because the models get quite complicated. There's lots of parameters.